Welcome to this tutorial. We want to see how we can transform second-order differential equations to homogeneous linear equations. So if you have not subscribed to this channel, kindly subscribe. You can even also share with your friends so that they get to know this knowledge. So how do we transform a second-order differential equation to homogeneous linear differential equation? This is how we do it. So if we have this kind of differential equation of that form, and if we let this solution function gx to be equal to 0, then automatically we have gotten homogeneous linear differential equation. That said, the solution here will depend on the functions of px and function qx. So these are now what will be giving us the kind of solution that we get. So let's now consider this a case. Let us consider a case whereby our px, function of px and qx are constants. So if they are constants, how do we deal with this? How do we deal with this? How do we deal with this? So homogeneous linear differential equations with constant coefficients. So automatically what we'll get is an homogeneous linear differential equation with constant coefficient. So in general, second order homogeneous linear differential equations with constant coefficients takes this form. So it's like our px and the qx we have given them to a, b, c as constant, and we make sure that the first derivative a coefficient is not equal to 0. It's not equal to 0, because the moment it becomes equal to 0, then we will not be talking about second order homogeneous, to reduce to first order. But in our case here, discussion is based on the first order homogeneous differential equation. So the solutions are of this form. So y will be given to that, Actually, this lambda should not be here. It should not be there. So it should be y equal to e lambda x. That's in general. So that if we differentiate this, we are going to get this. And if we get the second derivative, we get that. Okay. So it should be y equal to that. Sorry for that. Now substituting back to our homogeneous to our equation, to this, you'll find, you see now, yes, it's correct substitution. So you see that becomes true. What you need to do here is just to open and factor out. So if you factor out, you have this part here in brackets, and that is now what you need to put emphasis on, because it's what will help solve all the homogeneous linear equations. It's called characteristic or auxiliary equations. Auxiliary equation. Characteristic or auxiliary equation. So you'll see many of the tutorials that are in these the previous tutorial in solving this, I'll be substituting with lambda. So this lambda comes from here, taking y to be exponential of lambda x. So lambda is roots, stands for the root of this particular characteristic auxiliary equation. So how do you solve that kind of equation? So if you look at that function, You'll find this is just a polynomial. It's a polynomial equation, and it's to second order. It's a second order, so it is a quadratic equation. So that means quadratic formula is appropriate for solving that roots. You can get B, you can get C, you can get A. So what you need to do is just to substitute to this formula, and you solve, and therefore you get the respective roots. Okay, that's it. Let's meet to the next tutorial. Remember to subscribe and share to your friends. Bye for now.